In this presentation, I'm going to talk about the optical performance of live field display acquired both from simulation and empirical measurement, and on the actual display testbed. So we have been interested in live field displays, which is one of next generation 3D displays that viewers can accommodate at display 3D objects. And well, live field is a concept to represent light from a three-dimensional scene as rays, like each of which are specified by a position. For example, here it is SD here, and it's also with its direction, like theta and phi here. Then live field displays are meant to reproduce a live field by controlling the emitting light spatially and also angularly. And, well, importantly, live field displays may provide natural focusing effects to the viewers, which means the notorious vergence-accommodation conflict may be hopefully eliminated or at least reduced. So then this is how it works. There are live field display surface on the left and viewers, lens, eye lens, and the retina on the right. Then, first of all, a live field display must project two or more beams into the viewer's pupil to make this trick work. Then, now the display is showing or rendering a point here on the rendered depth with the red dashed line. Then, yeah, so if the eye accommodates at the display surface, like at the top, then each of the beams creates the focused image on the retina because it is optically focused. But individual images are laterally shifted thanks to the entering angles of the beams. Then the retinal image of this point will look like this, like shown like PSF or points per function. Then, if the eye accommodates at the rendered depth here, and then the individual images of this point for each beam will be defocused because the display is no longer in focus, but in position, these are perfectly overlapped on the retina, which ends up in much more compact points per function or point image of here. Then we expect this optically blurred but perfectly overlapped image to be recognized much more focused or having better image quality than optically focused but shifted images. So this is the trick of live field displays, and this is why it is not straightforward to evaluate whether this trick works in reality or how good received image quality will be and how to make the live field display for better image and focusing effects. So we have been handling with these questions in model-based and these are the same, model-based and measurement-based approaches. So so this is how we model a live field display to simulate the retinal images. The live field display is represented by an optical reference plane here, where conceptually directed light is coming from, like this. Then the retinal image of the render point here is a superposition of elemental point images, with each of which are generated by the beam coming from the reference plane, limited by the viewpoint, or I would say we call it viewpoint subaperture here, then ending up on the retina. Then we got the superposed image here, which is actually the summation or superposition over intensity here as a stack with respect to eye's focus or accommodation states. Then we further consider its frequency domain to think about how images are filtered throughout the display in the eye. So in this simplest model of live field displays, there are two critical parameters. One is the optical distance to this reference plane, and the other is the size and the number of these viewpoint subapertures. So we compared the simulated optical responses to measured responses. So the measurement was based on a method specified in ISO standard, and in which we do is pretty simple. We just show this test light field image consists of sharp edges rendered at 0 to 3 diopters, and which works as a step function. Then the camera with precise focus control will capture the displayed light field. Then what we get is edge spread function, or it is how spread edge. Yeah, it is spread edge on the camera sensor. Then after that, a few steps of computation finally gives the spatial frequency response, which means how image content is filtered throughout the light field display in the camera as a function of spatial frequency. Then this is what we got for both simulation and measurement. The 3D surface shows the measured responses, and the colored curve shows the simulated responses. Then all of the responses are stacked along the focusing depth of the focusing depth of the camera. Then I need to animate manually like this for different image depths, and then at this point you can roughly see the best responses are observed always around the image depth for both simulation and measurement. Then, which means the light field display was predicted to provide the focusing effect, and it actually apparently did in the measurement. So better visibility of focusing effect, we just took slices of the response at the gain of 0.1, which gives cutoff frequencies as a function of focusing depth of the camera. Then this is what we got. Solid curves at the bottom are major responses cutoff frequencies, and we can see the peaks around, always around each image depth, well, somehow shifting toward nearer depth, closer to the viewer, because having higher diopters. Well, still we conclude that the display seems reproducing focusing effect to at least to the camera, although errors up to, for example, here we can see 0.5 diopters of error. But, anyway, we conclude that display looks providing the focusing effect. Then we also plotted the cutoff frequencies in the simulated responses, which the dashed curves. Then, they don't show any error, quite simple. Then, obviously, a more visible difference will be the measured cutoff frequencies are much lower than the simulated ones, which means the measured responses were much worse than the simulation-based predictions. So same thing again. We found that best responses about when the camera is focusing at the image depth, and which means the display does provide the focusing effect. On the other hand, optical resolution was found quite limited. Even in the best response in the simulation, the response curve reaches 0 already at the point of 10 cycles per degree, which means the visual features finer than 10 CPD will be lost after filtering out through the display. So measured responses were even more limited than simulation. So for difference between simulation and measurement, there are several possible reasons for actually the large difference. The simulation includes only the optical distance to the reference plane and the profile of the viewpoint subapertures. And aberrations which includes chromatic aberration, are simply ignored. And also there could be an error in light field image processing pipeline. Then, well, we just simulated responses for individual viewpoints on Zmax, so it is ray tracing based, to see how aberrations affect the responses. Then, because we have an exact Zmax model of our light field displays, and ray tracing gives the responses that which gives the response that include the effect of optical aberrations. But, well, result is as shown, like indicating very little difference between the ideal model and the original model and the model with aberrations. So we suspect this is because of very small aperture size of the viewpoint, which lessens the effect of aberrations. And getting back to the original responses, small aperture size may be the principal factor of the limited optical resolution. Then we made another simulation in the original model with expanded viewpoint subapertures, and it is shown. These are shown as the red curves. Then you may see the red curves are much broader than the original blue curves. And also, this is clearly visible in cutoff frequencies between the simulations of original and the expanded subapertures. So what we conclude is that this, at least in simulation, expanding the subaperture size will clearly improve the responses. Okay, so let me summarize. We made simulation measurement-based study on light field display test bed, and we found the display does provide focusing effect at least to camera. Then we evaluate the optical resolution of the rendered light field image. Then simulated resolution was already quite limited, and the major responses were even worse. And we believe the principal factor for this should be small viewpoint subapertures. Then the final message, one of the final message would be this: in designing practical light field displays that is accommodative, larger subapertures may be more important than having more viewpoints. Okay, so this is all of my points. I'd like to thank to the research team for their support, and also to Dr. Madsen and Dr. Kvasa from Serial SA for their help. Thank you.
Thank you. Let's thank the speaker.